October 2025, MAVEN's atmospheric sensors detect something that shouldn't exist: nickel-rich particles flooding Mars's upper atmosphere at the exact moment. Interstellar visitor 3I Atlas passes 3.9 million kilometers away. That's 10 times the distance to our moon. Too far for any known physics to explain material transfer. Yet the timing is perfect to the hour. The spectral signature is unmistakable, and the concentration is 1,000 times what random cosmic dust could produce. Either 3 separate Mars missions simultaneously malfunctioned, or we just witnessed the first documented interstellar material release into a planetary atmosphere. But if material can be precisely delivered across millions of kilometers, what does that mean for Earth? The discovery began at 1447 UTC when MAVEN's neutral gas and ion mass spectrometer registered an anomalous spike in metallic ions at 180 kilometers altitude. Within minutes, the imaging ultraviolet spectrograph confirmed emission lines that had never appeared in 5 years of continuous monitoring. The signature was stark: nickel and magnesium in ratios that matched no known Martian process, no recorded solar wind event, and no catalogued meteoritic input. Mars Express caught it too. Its Aspera 3 instrument, designed to study atmospheric escape, suddenly showed ion densities surging to levels typically seen only during the most extreme solar storms. But space weather was calm. The sun showed no flares, no coronal mass ejections, nothing that could explain the sudden atmospheric disruption. The only variable was 3I Atlas passing through its closest approach to Mars at that exact window. By 1622 UTC, the Trace Gas Orbiter's atmospheric chemistry suite detected something even stranger. Carbon dioxide isotope ratios in the thermosphere had shifted by 2 parts per thousand, a change that would require either massive volcanic outgassing or the injection of external material with a completely different isotopic fingerprint. Mars has no active volcanism. The isotope shift peaked precisely when 3I Atlas crossed the point of minimum distance. 3 independent spacecraft, 5 different instruments, all recording the impossible at the same moment. The data was flagged for immediate analysis, but the calendar was working against them. Solar conjunction would begin October 8th, cutting off high-bandwidth communication with Mars for 2 weeks. Teams had less than 18 hours to capture and transmit as much raw data as possible. But those 18 hours would reveal something that makes the initial detection look mundane by comparison. The particles shouldn't have been there at all. Mars's upper atmosphere typically contains iron from micrometeorite ablation, sodium from rare impacts, and trace amounts of magnesium from solar wind sputtering. Nickel appears at concentrations of less than 1 part per billion, barely detectable even with the most sensitive instruments. On October 7th, nickel concentrations reached 1,000 parts per billion at 180 kilometers altitude, spreading downward in a pattern that defied atmospheric physics. The vertical distribution was wrong. Heavier metallic particles should concentrate lower in the atmosphere, pulled down by gravity. Instead, MAVEN tracked a top-heavy profile with peak concentrations in the thermosphere, thinning as the particles descended. It looked exactly like material being deposited from above, not lifted from below. The horizontal spread was even more puzzling. Instead of following Mars's atmospheric circulation patterns, the nickel cloud expanded in a perfect cone from a point source aligned with 3I Atlas's sky position. Temperature data added another impossibility. The particles were cold, nearly 100 Kelvin below the surrounding thermosphere. Fresh material from space should have been heated by atmospheric friction during entry. Cold particles suggested either an incredibly gentle deposition or material that had been deliberately cooled before release. Neither option fit any known natural mechanism. Most disturbing were the particle velocities. MAVEN's measurements showed the nickel atoms moving at 4.2 kilometers per second relative to Mars' atmosphere, far too slow for material naturally stripped from a comet at interstellar speeds, but perfectly matched to what you'd expect from a controlled release calculated to achieve atmospheric capture. The isotope signatures confirmed these weren't from Mars, weren't from typical solar system material, and certainly weren't instrumental artifacts. But identifying what they weren't was easier than explaining what they were. Space is vast and physics is unforgiving. For material to transfer from a comet to a planet's atmosphere across 3.9 million kilometers requires overcoming seemingly impossible odds. Solar wind typically disperses cometary particles in a broad cone stretching millions of kilometers wide. By the time that cone reaches Mars' distance, particle density drops to essentially zero. The inverse square law is brutal. Double the distance, quarter the density. At 3.9 million kilometers, natural dispersion would dilute any cometary material to undetectable traces. Magnetic field interactions offer another pathway. Charged particles from comets can follow interplanetary magnetic field lines, potentially creating streams of material between objects. But Mars has no global magnetic field to capture and funnel these particles. Its weak crustal magnetic anomalies cover less than 1% of the planet's surface, nowhere near enough to concentrate material to the observed densities. Dust dynamics make the problem worse. Cometary dust particles large enough to survive interplanetary transit move at tens of kilometers per second. At those speeds, they'd either skip off Mars' atmosphere like stones on water or vaporize instantly on contact, creating brief meteoric flashes, not the sustained cold particle injection observed by MAVEN. The only mechanism that fits the data is directed stream deposition, where material is deliberately aimed and velocity matched for atmospheric insertion. Think of it like the difference between spraying water from a hose in all directions versus using a precision nozzle to hit a specific target. Natural comets don't have precision nozzles. They shed material chaotically in all directions. Yet the numbers don't lie. The particle velocities, temperatures, and distributions all point to material that was somehow guided to Mars with surgical precision. The orbital mechanics make coincidence nearly impossible. 3I Atlas approached Mars from above the ecliptic plane at an angle of 87 degrees, almost perpendicular to the planet's orbit. Its velocity relative to Mars was 42 kilometers per second, fast enough to cross the diameter of Earth in 5 minutes. At closest approach, 3.9 million kilometers separated the two objects, a gulf so vast that light itself takes 13 seconds to cross it. The encounter window was brief. 3I Atlas entered Mars's Hill sphere, its gravitational zone of influence, at 11:30 UTC on October 7th and exited at 1945 UTC the same day. Just 8 hours where any gravitational interaction was theoretically possible, though at these distances and speeds, Mars's gravity could barely nudge the interstellar visitor's trajectory by a fraction of a degree. But the timing alignment was perfect. The atmospheric anomaly began exactly when 3I Atlas crossed the perpendicular point, the moment when its trajectory was closest to Mars' normal, creating the shortest possible path between objects. The particle injection peaked when the phase angle, the Sun-Mars comet alignment, hit 90 degrees, optimal for solar wind to potentially push material sideways toward Mars. Every geometric factor that could favor material transfer lined up within the same 2-hour window. Solar wind conditions were recorded by Mars Express throughout the encounter. Velocity, 380 kilometers per second. Density, 4.3 particles per cubic centimeter. Magnetic field strength, 5 nanoteslas. All normal values, nothing that would create unusual transport conditions. The interplanetary medium was quiet, making the material transfer even more inexplicable. The geometry suggests intention, but proving intention requires evidence of something even more extraordinary. The spectral data tells a story no one expected. MAVEN's imaging, ultraviolet spectrograph, captured emission lines at wavelengths that had never appeared in Mars' atmosphere. 232.0 nanometers and 341.5 nanometers, the distinctive double signature of nickel atoms transitioning between quantum energy states. But these weren't ordinary nickel emissions. The line widths were anomalously narrow, less than 0.1 nanometers, suggesting the atoms were moving in coordinated groups rather than randomly dispersed. The nickel-to-iron ratio broke all precedents. Solar system objects, from asteroids to comets, maintain nickel-to-iron ratios between 1.10 and 1.20, reflecting the primordial composition of the solar nebula. The particles in Mars' atmosphere showed a ratio of 3.1, nickel dominating iron by a factor that doesn't exist in any cataloged solar system body. This matched exactly the anomalous composition reported for 3I Atlas itself during its approach, creating a chemical fingerprint as unique as DNA. Carbon isotopes provided the smoking gun. The injected material showed a carbon-13 to carbon-12 ratio of 0.097, significantly depleted compared to Mars's atmospheric value of 0.01. This depletion suggests material formed in a different stellar environment, under different nucleosynthetic conditions. Interstellar material would show exactly this kind of isotopic deviation. Independent verification came from an unexpected source. The Mars Sample Return Preparation mission, still in orbit, carried an experimental mass spectrometer designed to test contamination protocols. It wasn't designed for atmospheric sampling, but its principal investigator made an emergency decision to point it upward during the anomaly. The preliminary data, transmitted just before solar conjunction, confirmed nickel concentrations and isotope ratios within 2% of MAVEN's measurements. 3 different spacecraft using completely different detection methods, all finding the same impossible chemistry. But chemistry was only half the story. The scientific community split into 3 camps within hours of the data release. The instrument error camp, led by veteran Mars researchers, argued that simultaneous malfunction or calibration, drift across multiple spacecraft, while unlikely, was still more probable than rewriting physics textbooks. They pointed to the 2019 methane controversy, when multiple Mars missions detected gas that later proved to be sensor contamination. But this time, the sensors were different types, on different spacecraft, built by different agencies. The natural phenomenon camp proposed a complex chain of coincidences. Perhaps 3I Atlas had fragmented days earlier, releasing a cloud of particles that happened to intersect Mars through pure chance. Solar wind could have compressed and guided this cloud, creating the illusion of directed transfer. The isotope anomalies might result from photochemical processes during the long journey through interplanetary space. Each piece was individually unlikely, but together they avoided invoking new physics. The directed release hypothesis gained traction among younger researchers. They argued the evidence pattern was too precise for natural processes. The velocity matching, the temperature anomaly, the narrow emission lines, the perfect timing, all suggested material specifically prepared and released for atmospheric capture. Some went further, proposing that 3I Atlas might be conducting deliberate atmospheric sampling or seeding across multiple solar system bodies. The debate intensified when someone noticed that Earth would pass through the same heliocentric longitude as the Mars encounter in its January 2026. If 3I Atlas was following a program, Earth might be next. NASA's Planetary Defense Coordination Office quietly began preparing contingency protocols while publicly maintaining that natural explanations remained most likely. But as solar conjunction approached, cutting off Mars communication, one final transmission would change everything. MAVEN executed emergency maneuvers with just hours remaining before solar conjunction. The spacecraft fired thrusters to lower its periapsis to 150 kilometers, deep into the particle cloud, risking increased atmospheric drag for direct sampling. In 3 aggressive passes, its mass spectrometer collected data that would take weeks to fully transmit back to Earth. The preliminary burst showed something unexpected: organic molecules, complex carbon chains that shouldn't survive in Mars' harsh upper atmosphere. Mars Reconnaissance Orbiter pivoted its high-rise camera, originally designed for surface geology, toward the limb of Mars's atmosphere. The images, compressed and transmitted in the final hours, showed a faint but distinct green air glow at wavelengths matching nickel excitation. The glow formed a cap over Mars' northern hemisphere, precisely where 3I Atlas had been positioned during closest approach. Image timestamps confirmed the glow intensified and faded in sync with the particle injection. Traced Gas Orbiter made a different choice. Instead of chasing the anomaly, it focused on establishing baseline measurements everywhere else, creating a control dataset to prove the localized nature of the event. This conservative approach would later prove crucial when skeptics claimed global contamination or systematic instrument error. The normal readings everywhere except the injection zone made the anomaly even more stark. But the most critical data remains locked behind solar conjunction. MAVEN's full mass spectrometry dataset, MRO's complete imaging sequence, and TGO's high-resolution atmospheric profiles sit in spacecraft memory, waiting for the communication window to reopen October 29th. NASA and ESA published what they could, but with 90% of the data still in transit, conclusions remain provisional. The evidence ladder is clear, but incomplete. Confirmed: anomalous particles in Mars' atmosphere, timed precisely with 3I Atlas's closest approach. Confirmed: isotopic signatures inconsistent with solar system material. Confirmed: distribution patterns that violate natural dispersion models. Contested: whether this represents deliberate release or an unknown natural mechanism. Unknown: the full composition of injected material and its ultimate fate in Mars' atmosphere. October 29th becomes the critical date. When Mars emerges from solar conjunction, the full datasets will finally download. Mass spectrometry will reveal whether organic molecules survived the injection. High-resolution imaging will show whether the particle cloud dispersed naturally or displayed further anomalous behavior. Most critically, continued monitoring will determine whether the foreign material persists or vanishes, whether it reaches the surface or remains trapped in the upper atmosphere. The bigger question looms as 3I Atlas approaches Earth's orbital distance in January 2026. Ground-based sensors are being calibrated, satellites tasked, and contingency plans drafted. If Earth's atmosphere shows similar injection signatures, the debate ends. Natural coincidence can't strike twice with such precision. The statistical impossibility that opened this story becomes statistical certainty of something far stranger. Either 3 Mars missions simultaneously malfunctioned in exactly the same way, producing false readings that perfectly mimicked an impossible event, or we've just witnessed the first confirmed interaction between interstellar technology and our solar system. The evidence points one direction, but science demands we wait for confirmation. The data arrives in 3 weeks. The answer might redefine our place in the cosmos. The only certainty is that 3i Atlas has already rewritten the textbooks, whether through new physics or new neighbors. October 7, 2025 marks either the greatest instrument error in space exploration history or First Contact's calling card, delivered directly into Mars' atmosphere with a precision that nature doesn't possess.